This is a machine built to intimidate.
This terrifying, growling, noisy beast that can smash its way through buildings, uproot trees, crush cars.
These things look invincible. You can't see any damage being done, and you leg it, and why not?
14 of these vehicles turning up will completely ruin your day. They are fearsome.
The tank, the bully on the battlefield. Inspiring affection.
This tank saved my life and those of the crew.
Constantly evolving in a race for supremacy.
In this never-ending battle between weapon and armour.
Its design driven by the enemy's desire to destroy it. Defying the doubters, the tank still holds its own on the battlefield. Perpetual testing, reinventing, in the search to build the ultimate. This is the Challenger 2, pride of the Royal Armoured Corps. 69 tons of precision-cut steel, an engine as powerful as 10 Land Rovers, and a gun that can annihilate targets miles away.
There's a lot of noise and dust and diesel fumes and confusion for us, considerably more for the enemy. These strike fear into the hearts of anyone who's sitting in a trench waiting to be attacked.
The tank is the culmination of nearly 100 years of evolution.
There are three components that make up a tank, that make a first-class tank, and they are protection, firepower and mobility. And one must have an equal balance between these to make the tank a superb fighting vehicle.
Mobility gives the tank its uniqueness as a weapon of war. It allows unrivaled command of the battlefield. Strip away the tank's armour and gun, and its true genius is revealed. The tank, as we would recognise it today, first rumbled into view in World War I. The British unleashed their new wonder weapon on an unsuspecting enemy.
One can almost imagine what it must have been like in 1916 when the Germans, peering out of their waterlogged trenches, saw these great armoured monsters trundling towards them. No sign of human beings, this terrifying, growling, noisy beast that can smash its way through buildings, uproot trees, crush cars with impunity.
The days of trench warfare were numbered.
The Germans were digging trenches at least 9 feet wide. So the designers solved the problem by literally increasing the size of the frame of the vehicle and then wrapping the tracks all the way around. And what it means is that on rough ground, this vehicle will present a tracked surface, a moving track, at virtually any angle. From nose down to nose in the air, there's always something to grip and keep it going.
Tracks have to withstand huge stresses. They have to be able to climb steep gradients, keep moving through water, and plough through desert sand. Track design has been much refined since World War I, but the big change came in the 1970s, and it's invisible. In 1916, tracks were made of cast iron. Today, they're a complex mix of steels.
We have to control the type of steel that we use in each individual part so that it's strong enough to do the job. And the way we can do that is by controlling the chemistry of the steel.
Some parts of the track have to be flexible, others demand pure hardness. Track technology has come a long way. This strength test shows just how far. 2 track links have been made that look virtually identical. One of modern steel, the other cast iron. Both will be tested to breaking point.
We would expect the modern track link material to sustain a load of around about 18 or 20 double-decker buses being loaded onto it in this central section.
First into the test rig is the cast iron track link. It buckles under a force of 21 tons. Next up is the modern steel track link. It fails at an impressive 40 tons, withstanding twice the force of the cast iron.
The historical material has failed catastrophically, and it's actually broken all the way through the link. Whereas the modern steel material, not only has it carried twice the load, but also it's been able to bend whilst it's carried that load before it's broken.
So track strength has increased massively since World War I. The other great advance has been in suspension.
In the First World War, tanks had no springs at all, and the big advance in suspension systems was that introduced by J. Walter Christie in the 20s.
J. Walter Christie was a freelance American tank designer, considered by many to be a genius, by others to be a complete maverick. And Christie's ideas for suspension were by far ahead of their time. There was nothing else like it in the world.
Now, if you can imagine that my forearm is a swinging metal arm attached to the tank here at the back and with a wheel roughly where my hand would be gripping there. That arm has bearing upon it an enormous coil spring. So, tank reaches a bump, wheel rises up, pushes up the arm, spring pushes it back down again. One of the characteristics of the Christie tank is the gap between what's known as the top run of the track and the tim work, enabling the wheels to move very freely. So with a tank like this, you could easily do 30 miles an hour across country quite comfortably. Indeed, in 1932, Christie had a tank doing 60 miles an hour over rough ground. Nearly finished off the driver, but at least it could do it.
A 30-foot trench in front, and she's over.
While steel technology transformed tracks, independent suspension turned the tank into a highly mobile fighting machine. Tank design is constantly evolving, but one problem has never gone away. A tank has to be able to take a hit. In World War II, British tank designers believed sheer thickness of steel was the key to protection. Come D-Day, their hopes were pinned on the Churchill tank.
It was the most heavily armoured tank that the British had at that time. And the front plate was about 6 inches thick.
Dennis Kerner was just 18 when he joined the Royal Armoured Corps. In August 1944, in its first real battle, 2/3 of his regiment's tanks were knocked out in barely 2 days.
I've seen the driver and the co-driver, after their tank had burnt out, trying to escape through the escape hatch, and they were burnt to a cinder, and all you could see was the grey matter of their bones as they'd stretched out, and that is not a pretty sight. When we came up against these German tanks, you were not prepared for what they could do. I mean, our shells would just bounce off.
But why were the shells bouncing off? The answer? An innovation the Germans had copied from the Russians, and one still used in virtually every tank today. A simple but brilliant idea. Slope a tank's armour, and its thickness is effectively increased.
I've got 3 pieces of identical armour here. In this one, a projectile can defeat that if it gets across the width. In this one, because it's sloped, the effective width has now increased. And for any projectile, it may not get through. Now, if you slope it even further, you might be protected again by the projectile not being able to penetrate, but ricocheting away off the surface.
Testing at a firing range should show why sloped armour is so effective.
Now what we're going to fire at is this. It's armour plate, about 15 millimetres thick, made of solid steel. Now, although that represents quite a challenge, it's my guess that this bullet, travelling at 890 metres per second, when it hits it, will penetrate.
Test 1. A piece of armour positioned vertically. Test 2. Armour sloped at an angle of 30 degrees. And finally, test 3 at 60 degrees.
This is the first plate that we fired at vertically. And what we've got is a clean penetration. Hole at the front, clean hole straight the way through to the back.
Here's the impact again, viewed this time through an ultra-high-speed camera. The vulnerability of the vertical armour is plain to see.
Where we put the plate at 30 degrees to the vertical, we've actually caught the bullet within the armour, and you can see the base of it there. And we've got a bulge at the back, but no penetration. So it wouldn't have caused any damage on the inside.
On the high-speed images, it's clear there's no penetration.
And lastly, where we slope the armour right back at 60 degrees, we've got a dent, but there's no bullet. It's ricocheted clean away. And again, no damage to the inside. So the effect is that by sloping the armour, we've protected the crew, although we've only kept the same thickness of steel.
But new armour designs always provoke a counterpunch. Before World War II was over, an anti-tank weapon was invented that could penetrate even the best sloped armour: the shaped charge. Tank armour design has to be constantly rethought as new weapons are devised to defeat it. Most deadly of all is the shaped charge. Invented at the end of World War II, the shaped charge was unchallenged for more than 20 years. But in 1967, a chance discovery tilted the balance back in favour of the tank. A young German scientist was experimenting with captured Egyptian tanks in the desert.
It was after the Six-Day War, where Israel have destroyed a lot of Russian tanks from the Egyptian force, typically T-54 and T-55 tanks. I wanted to see the effectiveness of my warheads on real targets.
Manfred Held was testing shaped charges against tank armour, but he was puzzled by the results.
This was a surprise that my shaped charges was not able to penetrate the total turret, and I wanted to find out at once what was happening.
He discovered that there was still live ammunition in some of the tanks. As the shaped charge penetrated the armour, it hit shell cartridges on the inside, causing them to explode.
After the test, I found no impacts on the other side, only the entrance hole, and burned out cartridges, but nothing else on the other side. And this was against my prediction.
Manfred realised he was on the verge of an important discovery. He inserted high explosive between two metal plates and placed it on the tank's armour. The impact of the shaped charge was drastically reduced. Manfred patented his design in 1970. It would revolutionise tank protection. He had invented what's now known as explosive reactive armour.
This is a shaped charge. Now we're going to fire that against these steel plates. And between the two, I've placed a block of polystyrene that will give it the standoff required to give it the most effect. Now across here, I've constructed the same sort of experiment, but on this occasion, between the two, I've inserted a layer of explosive reactive armour. Now this is constructed from two steel plates, but sandwiched between is a sheet of plastic high explosive. When the jet fires down into those plates, it'll detonate the plastic explosive and the two plates will fly apart. Now the effect is that the jet has to cut its way through these plates and is essentially disrupted by that and will hopefully show far less penetration down in the armour. Now, as we saw, there was a huge release of energy in those explosions. Massive damage done. This was the one where the shaped charge did a direct attack onto steel blocks. And we've had penetration all the way through to this block here. Now, in this set, where we had the explosive reactive armour, we've only got penetration down to the 5th block. We've saved 3 whole blocks of penetration. But ultimately, the explosive reactive armour has saved that crew's life.
Explosive reactive armour gave tank protection a whole new dimension and a crucial edge over the weapons designed to penetrate it. A tank's main purpose is to take and defend ground. A powerful and accurate gun is vital. Wartime newsreels often show tanks firing on the move. The reality was that few tanks could fire accurately like this. In fact, most fired from a static position.
Basic principle of firing a gun from a moving object is not a new one. The Royal Navy had this problem hundreds of years ago when it tried to fire cannon against other ships on a moving sea. And it's really just the same problem that we have in tanks. In the Second World War, it relied on great skill and experience of the gunners to achieve some sort of accuracy.
American tank designers were working on the ultimate solution. By 1945, they'd introduced stabilization systems on their tank guns. Today, these use gyroscopes to sense the tiniest movement and correct it with sophisticated stabilizers.
That enables us to lay the gun onto a fixed point, and the gun will remain pointing at that point regardless of what the vehicle is doing. So even if the vehicle is moving along an extremely bumpy or undulating surface, the gun still remains fixed on the point of aim.
So modern battle tanks can hit targets several miles away with pinpoint accuracy. Whether moving or still. Supreme weaponry makes today's tank a fearsome machine. To reach speeds of nearly 40 miles per hour, the Challenger 2 needs a mighty engine. 1,200 brake horsepower drives these monsters along. But power and speed are useless if a tank keeps breaking down. A key lesson in tank engine design was learnt in the winter of 1941. The German armoured divisions were fighting on the Eastern Front. To their dismay, their once all-conquering panzers ground to a halt.
The onset, of course, of the Russian winter completely broke down the German armoured thrust. The Germans suddenly found that their entire tanks' cooling and lubricant systems and fuel supply became completely iced up in temperatures of minus 40 and 50.
The myth of German tank invincibility had exploded. Their sophisticated engines failed when the mercury plummeted. The much simpler Russian tanks just kept going.
This is the Russian T-34, probably the key tank of the entire Second World War. The engine is the crudest, toughest old V12 diesel you could possibly imagine, a thing that will slog on in the worst possible conditions.
Nearly 60 years later, Russian tank engines are still going strong. One of them in this quiet corner of Devon. Preston Isaacs collects tanks. This is one of his favourites. A genuine World War II T-34. Ex-tank commander Mark Corby has come to get a feel for this rough but reliable piece of Russian engineering.
Carefully does it. Very elegant.
God, it's brutally basic in here, isn't it?
Yes, welcome to a luxury vehicle.
Where's all the padding gone? I mean, what's it like this?
It's nice enough to bang your head on, but everything is very basic. Don't waste time grinding bits off. Make it in a hurry, make it work, and that's all you need it to do.
This is the, what, the gear lever here?
Gear lever. That's your machine gun.
Right, yeah. Oh, yeah.
And that's your sole view of the world, what you can see through that.
Okay. Shall we go?
Show me the way.
Okay.
The T-34 signalled a turning point. From now on, simplicity and reliability would be the key ingredients. Today, most modern tanks have diesel engines, but Mother Nature keeps on throwing new spanners into the works. Oman 2002. The British Army is on a massive exercise in the desert, but its tanks keep breaking down. At the Armoured Trials and Development Unit, they tried to find out why.
Basically what was happening was that the dust, which is very fine sand, was coming up between the road wheels and swirling up underneath the skirts and on top of this air intake and basically being sucked straight into the engine.
Tanks have been successfully operating in the desert through 2 world wars. So why was the state-of-the-art Challenger 2 running into trouble?
The normal wind-blown sand is quite coarse and each particle is very clearly visible. But when that sand is trafficked and vehicles have been passing across it for a while, it becomes extremely fine and powdery, almost like flour. And it is this fine dust that is what was posing the problems to the vehicles.
The wrong kind of sand? Sand in Oman is not the same as that in North Africa. The aerodynamics of the Challenger 2 was creating a wind vortex that drove this superfine sand into the engine.
Whenever we go to war, we suit ourselves up in this armour, and just by doing that, we change the dust vortices to such a degree that we move them back a degree, but we still had that problem. So we came up with this idea here, which essentially is a number of canvas skirts joined together with some clips. And what that does is it forces those dust vortices down and keeps them down as the tank moves forward until the tank has passed over and they appear behind the tank. So you get a great plume of dust behind the tank, but not being sucked into the engine. So a simple solution, but one that we're very proud of.
Ingenious yet simple answers to complicated problems. This is the tank of today, but what is its future?
The big question, of course, is the tank still relevant then? Is it really an obsolete piece of junk that can be shot to pieces by air power?
But aircraft have their own limitations.
You can never dominate the ground really by air power. You can make a mess of it, but you can't really dominate it. If you want to dominate the centre of a city, you've got to have a tank in there.
So the tank has timeless qualities.
Rumours of its demise are much exaggerated. I have to say this thing will turn up on a battlefield for the foreseeable future.
But change is still on the cards.
One can see far more concentration, I suspect, on lighter, more mobile vehicles that are air-portable for a start, to get to a trouble spot quickly. And I do think what we will see is the tank being upgraded and improved rather than redesigned.
Evolution continues, but the essentials remain the same.